My family has a strong tradition in producing wine, and I remember when I was a child, we used to gather all the family because we had to go on to the field, to the wine field, and collect the grapes, right? And we had a really, really huge field full of these grapes. So I was always afraid because it was so huge. How are we going to collect this? And then I remember my grandmother. She used to say that many hands make light work, or the idea that when you have a job that is that big, the more people will join you, the better and the faster probably you will do this. And this is kind of the idea of multi-threading that we get here. And the idea of splitting work, it's not really new. One of the first multi-threaded systems was created already in 1950s. Of course, the level of multi-threading was very simple at that time, but during the generations, we have evolved and really improved the theory and implementation of multi-threading that we use today. What does really multi-threading mean? If we open Wikipedia, we would read the following. Multi-threading is the ability of a central processing unit to provide multiple threads of execution concurrently. But I think in order to make this definition a bit more complete, we need to understand what the threads of execution is. So we go on in Wikipedia and then we read that a thread of execution is the smallest sequence of programmed instructions that can be managed independently by a scheduler. Well, now I'm a bit more visual person, so if I try to put this on image, it could be something like this. So we have a box where our central processing unit is. We have the operating system scheduler in front of it, and then we have all these threads in front of that. And then the scheduler used something called context switching in order to run this on the same CPU. It's that simple. However, multi-threading is often really perplexed with some other definitions, and these are multitasking and multiprocessing. So what is really the difference there? If we start with multitasking, this is really the ability of your operating system to run different tasks or processes concurrently on the same CPU. And this is something that we are very used to. On your machine, you can run the browser, you can run Visual Studio Code, or maybe your word processor, etc. So we have these different tasks running concurrently on your CPU. Multiprocessing is really adding more CPUs or more cores in order to improve the computing efficiency of your operating system on your code. So really there is scaling the CPUs up. And then multi-threading is inside the only one single process where we can create these small threads of execution that are kind of separate and almost independent because they have each thread has a stack, register, program counter, but they do share the memory of this process. And that's a very important concept that we are going to look inside in a while. When shall we use this? One of the very, very basic examples that we know of, it's when we have a graphical user interface. It usually runs on the so-called main thread. And then you know that if you want to perform some manipulation, let's say sending data over the network or fetching something from the internet, these tasks really require some time to complete. And if you run them on this thread, they would block the thread, and it will call, of course, bad user experience at the end. So usually this kind of task you want to put in a separate background thread. In case where you have really specific CPU-bound computation, there you really want to go on the separate process to do this. And the difference here is that threads are really easy and cheap to create, while processes are a bit more, it takes a little more to create, but they give you some other things in terms of computation. One very interesting thing that we start observing when we enter the world of threading is that our applications need to be written in a specific way if we want to use threading. And there is this very popular tweet from Net Bachelor that says that some people have a problem and they think, hey, I know, I'll use threads. And they too have problems afterwards, right? And that's because threads really use the same memory of your process, and this is something that we developers forget. WebAssembly is a compile target for the web. It allows us to compile from languages like C, C++, Rust, and run this into your browser and Node.js environment. And the idea here is that if we had code written in, let's say, C, I can compile this to native on my Windows machine or my Linux, and then I can use exactly same source code to compile this WebAssembly and run this into the browser or a Node.js environment. So this is the idea of WebAssembly, because we extend what compilers have today. We add a new compilation target for the web or Node.js. The question now is, can we really use threads in WebAssembly? Because if you think of languages like C and C++, threads are something that we know they exist there, we use them. How does this translate to something we run into the browser? To answer this question, first we need to take a look at what the architecture for the web is today and what JavaScript has achieved during the years. JavaScript currently is single-threaded, which means that in the browser you have one thread doing everything for your JavaScript. And this means that if we want to run WebAssembly, calls to WebAssembly will be blocking. So if you had a very simple application to load the WebAssembly module and run this with WebAssembly.instantiate, we can call one of the exported methods from WebAssembly. This will be a blocking call. So if you do some kind of computation there, the browser will freeze. And that's not really nice for our end users. We don't really want to do this. Now, the new kit in the block is called Web Workers, and that's not really new for us, but this is something that we can use in different ways. And Web Workers are the way to do threading in the web. How does this work? Well, if we have our main thread, there we can create a worker thread and give it some JavaScript to execute. And now we have a separate background thread running completely independently. However, because most of the JavaScript code that is written is not really thread safe, because we know the JavaScript is single-threaded. And in order not to break this, worker threads and main threads are completely isolated, so they don't share anything. The only way to communicate between these threads is using messaging. So the main thread can post messages to the worker thread can receive these messages and then reply with another messages back and forth. There is one thing about this mechanism, and then it's these messages are completely independent, which means that the message is serialized and copied over every time you post it from one thread to the other, because they don't share, the threads don't share anything. So in order to keep this, we need to serialize the message, then deserialize it in the thread and put it into the memory again. This process can be very inefficient if you have a large stream of bytes that you want to pass between the threads, because it will really slow and kind of defeat the idea of splitting tasks behind the threads. What we have as a support of WebAssembly in the browsers now is called MVP, or version 1. This is the first initial version of MVP that most of the browser vendors that do implement today. And this one doesn't really contain the idea of threads. However, there are post-MVP features and proposals that are currently into consideration. And one of these is really about threads. So there is something going on there. WebAssembly specification process follows what we know from JavaScript. So there are different stages of these proposals. So now the thread proposal is in stage 2, which means that they are already implementations, as we are going to see. What does this include? We have 3 main parts of what WebAssembly threads are. The first one is called shared linear memory. And this is the idea of sharing memory between the threads, as we know from C and C++ and other languages that support threads. Then we have a set of atomic operations that we can perform on this shared memory. And the third one is the ability to basically suspend and awake threads when you need that to do. Let's take a look at how this would be applied today. What WebAssembly uses of memory is called the linear memory. It's basically an array in JavaScript. So this is a JavaScript abstraction that sends a different set of bits to WebAssembly to work with. So if you know in C and C++, all the work you do in the memory, it translates just to a simple array where you have indices instead of pointers to a real memory. And the way we create this kind of memory in JavaScript is by using the special constructor called WebAssembly.memory, where we can give it an initial size, we can give it a maximum size, and then when instantiating the module or WebAssembly application, you can import this memory into that. So this is JavaScript part. Now, the way to do this is WebAssembly is if we had our module up there, we can declare that this module requires an import of memory with a certain size. And this will fail if you don't provide this one. As you know, WebAssembly comes in two formats, textual format and binary format. But I mean, the binary format is just numbers, and we are human, so we like seeing text. So we'll focus on the textual format here, what you're going to see in the rest of the presentation. So now the shared memory really extends this by adding a new Boolean to the constructor of WebAssembly memory. It's a shared toggle. So if you set this to true and then import this in creation, then your WebAssembly module would declare basically the shared thing there. So it's only this flag that extends and marks this memory as to be shared. Now, what this shared abstraction really does is using something called shared array buffer under the hood. And this is the way to share data between threads in JavaScript. The way it works is that now if I have threads, if I have my main thread and then I have a worker thread, I can initialize my shared array buffer, put some data in it, and now this data is not going to be copied over to my thread. This is really a shared part of the memory that both threads are going to point towards. So now we have this sharing capability that we need when working with threads. However, there is one problem. And maybe some of you remember some time ago we had these two issues, vulnerabilities, Spectre and Meltdown. And what it caused was that many browser vendors, they had to disable shared array buffer because it was enabling really these two vulnerabilities. At this time, people started really discussing what is going to happen with WebAssembly now. I mean, is it really safe to compile from C, like language used to compile to your native machine, to compile this to the web browser? And the good thing is that WebAssembly follows the security architecture of JavaScript. It runs in a sandbox, and it kind of follows all these things that we have done during the development of the web during the years. So it's not something that is going to cause troubles for us. However, what browser did was they disabled the shared array buffer, and this kind of delayed the thread proposal development. What is happening now is the opposite. Browser vendors are starting to re-enable this because they have fixed the problem. And so far, the only browser that has done this is Chrome. So it is enabled in Chrome. All the other browsers, if you go on caniuse.com, you can see that actually all the modern browsers have implementation for shared array buffer. The difference is that it's hidden behind a feature toggle. So you need to enable it manually if you really want to use it. It's only Chrome that has this enabled by default right now. When we have shared memory, we can go in something very, very weird. It is very common, let's say, that we want to have a kind of counter between our threads, and each thread should kind of increment it only one. But at the end, you expect this counter to be incremented by one from each thread. However, when we have this shared memory, what can happen is, because we can't really know when the context will be switched, so we can't really know when our line of code will be executed. So what we can go into is that two threads read the same value and then kind of update the same value again instead of having it 2 times in a row. So to prevent this, we need some synchronization mechanism. We need kind of locking on this value until it's updated. And this is the idea of atomic operations. They provide us a set of operations that's only one. And this could be, for example, loading and storing of data to the memory, so that it happens as atomic operation. Then we have read, modify, write, which is exactly this. Take a value from the memory, update it, and then write it back as one operation, so that we know that it's going to happen. And then we have compare exchange, which is basically taking a value from the memory, exchanging with another one in certain condition, and then write it back. So we having these atomic operations, we can perform operations on the shared memory in a trace-safe manner. And then the last set are these wait not fee operators that allow us to suspend the thread, as we know, and then wake it up later when we need it. And we can call this atomic wait and atomic notify and giving it a same address in the memory which will be used for that. So now I have prepared a short demo to see how this really works into with WebAssembly. What exactly we can do with it. So I have created a very simple application here where I have a matrix. I have a matrix with certain number of cells, and then I want to create a simple application written in C++, and this application will get the number of cells, and it has to paint these cells. So it has to generate a color and paint each of these cells. And I can span as many threads as I want to. And let's see what is going to happen. So if I start with just one thread, it is going to take some time now because I have put some fake computation there. So, it took like 4 seconds to kind of color these cells in some random color. Let's try to see how the code looks like. So, this is written in C++. It's not my strongest language. So if you feel intimidated, please excuse me for that. But the idea here is that I have one function, color cells, that gets worker ID, it gets the matrix size, and it should return how many cells it has painted in some random color, right? And then I have my wasm worker. The way it does is when it gets a message, it is going to instantiate the WebAssembly module, and then it's going to call this function color cells with the exact results. And then at the end, it will post a message back to the main thread with the worker ID and the number of colored cells. So it's very simple. So let's try this. I have created a short script to compile this, and I'm using something called mscripton. And mscripton is really an open source tool chain for compiling from C and C++ to WebAssembly. And this is how the code looks like. So let's try to see what is going to happen. So I can compile this. And if I go, so this code will generate actually 2 files from it. It will generate the WebAssembly binary format, and it will also generate the WebAssembly textual format. So what we're going to see now is the WebAssembly textual format. So you can see it's a pretty long, file containing all this logic optimized in a different ways. But what we're interested in is to see the import of the memory. So you can see so far, this memory, I haven't really set to mscripton that I want a shared memory. So what I'm going to do is I'll just add this Boolean flag here at the end to say that, hey, I want you to import a shared memory for me. And then, now what I want to do is I want to compile this textual format to the binary format. And to do this, I'm using another tool called WhatWasm. It's part of the WebAssembly binary toolkit. It's a really toolkit of different tools for that. And here I can set at the end, please enable threads for that. So it has supports for compiling about threads. So if I try to compile this again, then it will update my WebAssembly. And this is exactly what I'm getting here. So this is the result of this shared memory compilation. All right, so this is with 2. Let's try to run this with 2 threads to see how it's going to happen. So you can see now that now we have 2 colors, completely random colors. However, there is something that you may notice that it's not really correct here. I mean, the 2 threads, they claim they have colored 10 cells, but I have only 9 cells in my matrix, right? I have 3 by 3. So someone lies here, right? If I try to run it some more times, I could get, so it's 10 times again. So someone is really lying here for me. And the reason is because we have this shared memory. So those threads are really kind of overlapping each other in the coloring process and then claiming, hey, I colored this cell, and then the other one, hey, I colored it too. But this was not the case because I wanted only the first one to color it, and then the other one should skip this cell afterwards. So in order to do this, we need some synchronization, or we need to use some of these atomic operations for that. And what it is here is that I had created one switch here that in my C++ program, I can actually have some synchronization using mutexes. This is a very standard way to lock access to something shared. So if I try to compile this again, then we are going to get some new things. Let's take a look again at the generated WebAssembly file. So you can see now, because mscripten doesn't know how to compile this. I mean, mscripten doesn't really know how to compile to using threads so far, unless I tell it. So what it says is, hey, I have these functions at the end. I mean, it uses this mutex library from the standard library set, but it doesn't know how to implement this. So it requires you as a developer to provide implementation of these two functions to lock a mutex and to unlock a given address, right? So what we're going to do is first, of course, we are going to add again the shared Boolean flag here. And then I'm going to remove this because I'm going to get implementation for them. And I have stolen this implementation. It's very naive implementation of locking and unlocking mutexes, which you can find on the official WebAssembly threads proposal site. So what it does, if we try to look here, is that it uses exactly what we know, uses this atomic wait that we show, so we can kind of suspend a thread, and then we can wait for it. So if you come here, you can see now atomic notify, instead of giving it a central address. So it uses these smaller primitives that we get from the WebAssembly threads, and it kind of incorporates them into a bigger functions to lock and unlock mutexes. So I can now copy all these, and I can put it, let's say, somewhere here in between. And now I can try to compile this to WebAssembly. And now, hopefully, if I start this a couple of times, I shouldn't get any issues anymore, because now you can see it's 9. And because you can't really know when it's going to happen. But now we have synchronization of these shared parts of the memory, and this shouldn't be an issue. But now another question, do threads really help me with this? Now I have put some simulation computation in my C++ code that you didn't see. It's basically running some computation like thousands of times just to simulate something randomly for that. And what we can do now is, of course, we can increase the number of threads to see if our computation is getting really, really faster in that case. Let's try to run this with a bit bigger matrix. Let's say 10 by 3. So with 2 threads, this is going to take probably, let's see, maybe 10 or just 6 seconds. That's not that bad. Let's put this to 5. This is really going to be faster. It's actually taking longer. What about if we put this to 3? And like increasing the number of threads don't really help you all the time. There is a certain moment in your computation that increasing number of threads makes things slower. And the reason for this is that you have synchronization and the threads have to wait each other, right? So this is really about finding the right balance between how many threads I should do and then what synchronization mechanisms I need in my code. So you can see this is really crazy, taking 13 seconds just for that. So maybe 2 is kind of optimal. For 6 seconds, it's not that bad for this kind of metrics. Oh, it's avant. Yeah, 2 threads seem to be pretty well for this one. And now I've been modifying this by hand. This is not how we are supposed to do this. You can imagine that if you had a big code base written in C++ that uses threads, you don't really want to go that low level in order to be able to use threads. And the cool thing is that mscripten, this open source compiler tool, allows us to do this. But I didn't enable this so that I wanted to show you all the details out there. But we can do something like this. If we say to mscripten, hey, please take the source code, and then we can use these switches to use bit threads, then we can automatically get all these things created for us. So we'll get one HTML file, we'll get a JavaScript file, we'll get a worker file automatically with all the code, all the synchronization, all the shared memory injected and stuff like this. So we get really things out of the box. That. Now, multithreading is a really interesting concept. It's something that we want to use in order to kind of make our applications better, work better for our end users. But as you see on the picture here with the docs, if you expect that one thread will only go, or one doc will only go into its own dish, this is not going to happen because this is something controlled by the schedule. We can't really arrange when threads are going to execute, and they are going to mix around your application. So using threads, it's a solution to one problem, but then it creates some other problems that we as developers have to be aware of. What I believe with WebAssembly is that now we have a standardized way to reuse code that contains threads and put this into the web environment. We don't have this one-to-one mapping because threads in the operating system work in a different way as in the web, where we have web workers. But we do have a way to reuse code written in other low-level languages, which is one of the benefits of using WebAssembly and that. And I really do believe that future belongs to those who can compile. My name is Boyan. Thank you so much for being here today.